everyone, today we're going to solve longest increasing subsequence problem. Given an integer array nums, we should return the length of the longest strictly increasing subsequence. Here's an example. The output for this input should be 6 because we have 6 increasing numbers and they don't have to be contiguous. As you can see, you can jump over the values, but they have to appear in the same order as in original array. Let's look at the problem analysis, and we're gonna solve the problem by using applying dynamic programming. I'll explain what it means later. And time complexity will be O(n) squared, space complexity O(n), and it's gonna be a moderate exercise. And there is an algorithm more performant which executes an n log n, but it's more like a Jedi level, so it's a little bit more complicated. And on the right we have a nice representation of time and space complexity for different algorithms. So here's our time complexity, which is acceptable. As you can see, those kind of algorithms are considered impractical because they perform very badly for high input sizes. And what's nice about this diagram is that we have a pair of algorithms, n log n and O(n), which kind of perform very similar. So if you have n log n, it's kind of almost as good as O(n) algorithm. Same goes for O log n and constant time algorithms. As you can see, O log n is very good algorithm because log n function grows very slowly. So what is dynamic programming? We have this nice Yoda quote: by reusing computed results, dynamic programming eliminates redundancy. Think of dynamic programming as building something big using smaller building blocks, and each block represents a smaller problem that we solve individually, and then we combine the solutions to solve bigger problems. I know, guys, this is very abstract, but let's look at our example. So here we have an input array. Let's initialize our solution array, LIS, longest increasing subsequence, with ones, because each node by itself is considered as one, so it's a good initial value. Then we define our small problem. This is just for a single element. We don't have to consider any other elements. We just need to solve it for one element. And the solution is simply 1, because one element counts as 1. And this is going to be our base solution with which we're going to solve our problem. So we move our candidate to the right, and actually our algorithm, when implemented code, would start candidate at index 1, because for index 0 it's already solved, it's 1 always. The algorithm will go as follows. It will first check the condition if array at solved index, the value, is less than a value of the array at candidate index. This is to ensure we have an increasing subsequence. In this case, you can see 10 is less than 22. This condition is satisfied, and then we need to check if our solved LIS plus 1, because we need to account for candidate, is greater than wherever is being stored in LIS for candidate. And right now 2 is greater than 1, so 1 plus 1 is 2, greater than 1, though we need to update candidate cache. This is it. And then we continue the same manner. We move candidate to the right, we will run our LIS, or solved index, from 0 up until the candidate, and we'll check those conditions. And here you can see that the first condition is not true because 10 is greater than 9. We have actually decreasing subsequence, and it's no good. We won't even check the second condition. Of course, we're not going to update the candidate LIS cache. We move to 22, our solved index. Same here, 22 is greater than 9. We won't do anything. We move candidate to 33, and now we see that all values to the left are satisfying the first condition. They're all less than 33. This is why we need to only check the second condition. So 1 plus 1, so 1 plus new candidate, which is 1, is it greater than the value currently stored in LIS? Yes, it is. So we update it, move solve to the next one. 2 plus 1 is greater than 2. Yes, it is. So we update it to 3. 1 plus 1 is greater than 3. No, we don't do anything. Move candidate. And we continue in the same manner for each element of the array. We move candidate, we run our solved pointer from left to the candidate, and let's see the final iteration just to put everything together. So we are at candidate 80, solved is starting from 0 and will run until the candidate. We can see that all values in the array are less than candidate value. Again, first condition checks. We only need to consider LIS cache. Okay, 1 plus 1 is greater than 1, update the candidate cache, move to the next. 2 plus 1 is greater than 2, update the cache. 1 plus 1 is not greater, 3 plus 1 is greater than the candidate cache. 2 plus 1 is 3, which is less than 4, don't do anything. 4 plus 1, we need to update the cache. And 4 plus 1 again is 5, but we already have 5, so we don't do anything. And finally, 5 plus 1 is 6, which is greater than the value we store. We update the cache, and we run our candidate index to the end of the array. Finally, we need just to find the maximum value of our LIS solution. For this problem, it's 6. It just turns out to be the last value. Right, let me copy and paste generated test cases, and let's have a look. We have test cases in the requested format, LIS solution, given empty array, then 0, looks nice. Given array with single element, then 1. And array with multiple elements, this is our bread and butter test case. Array with all same elements, then 1. Perfect, because we don't have an increasing subsequence in this case. Array with decreasing elements, then also 1. And array with ascending elements, then length equals array size. Yes, if we have all ascending, I would like to add the following test case. Given array with ascending elements and duplicates, then expected size, right? I will duplicate some elements, and here we also expect the number 5, because yeah, duplicates should have no effect on the solution. Let's run our test case and see what we have so far. It's always a good thing to execute test cases. By the way, I'm using IntelliJ IDEA. Like they say, some people have IDEA and some people have no idea. So we have one passing test, not surprisingly, because this is the test for empty array that should return 0 subsequence. And ChatGPT generated code returns 0, so this is what we have, and all other tests are failing. Okay, let's start implementing the solution. So I would like to start with a simple guard clause, checking the length of our input array. If it's 0, we return 0. We don't have to worry about it anymore. Then we will initialize our LIS cache that will have the same size as the input array. This is where our dynamic programming solutions will be stored. We need to fill it with ones by using arrays fill. Then we start our main loop, and in IntelliJ I can type for I. It will create the loop for me for I, and it will run from 1 until the length of the array. And by the way, we're starting from 1 because, like we discussed, we have a solution for I0. And I also prefer to rename this to candidate. Then we start the second loop. I'm typing for I. Let's call it J up until candidate. So here I would also like to rename it to solved index. We need To check if it's an increasing subsequence, I can type if nums at solved, which is before, is less than nums for candidate, and I can put my cursor at the end of the nums candidate expression, type var. It will allow me to extract the expression into a variable, which I would like to call increasing. So if increasing, we simply update the ls cache for candidate to be the maximum of the two, right? We need to initiate a fight between existing candidate and ls solved plus 1. So this existing ls result fights versus solved result plus 1. Whichever wins will end up in the least candidate array. This looks great, and in the end we have to pick out the maximum. Again, I'm using streams API to find the maximum. I just need to tell the streams API, just give me the max, and as you can see, the max returns optional int, and it's never good to simply do like get as int, because if there are no values, and we can check what it throws, it will throw no such element. To prevent this, always use or else for all optionals you're dealing with, just or else null. Let's run our test cases one more time, and hopefully it will pass. Yeah, everything is passing. Again, look at this. We initialized the ls cache. We are looping through candidate indexes, starting from 1, because for 0 the problem is solved, it's 1, and we run our solved index from 0 until candidate each time, and we ensure it's an increasing subsequence. We find the maximum of the existing candidate cache value and solved value plus 1. And by the way, having these two for loops, this is what gives our solution time and squared complexity. And finally, we are finding the maximum value.